Hello friends, welcome to the today's session. In this session, we are going to discuss about multi-level index, also called as dynamic indexing. So what is a dynamic indexing? Why we are calling it as a multi-level indexing? What is a dynamic? Why we are calling it as multi-level indexing and dynamic indexing? We will see in this lecture. So as we all know that B tree and B plus trees or any kind of tree you consider as far as database management system consider they are called indexes only. So why there is a requirement of index in order to retrieval the data very faster. So if you not use the concept of indexing, then what is going to happen? Your data retrieval are bit slower. That's why vast database like Aadhaar database, IRCTC database, or any kind of database which has got a huge number of a million of records, then searching is a very big difficult. In order to get the searching of the record in a quicker manner, then there is a requirement of indexes. You see, for example, you go to the any bank and ask your details by saying your bank account number, they're able to give you your details within seconds, nanoseconds, the data can be retrieved. Or another real-time example you consider, you go to ATM, just insert your code, then it able to detect your code and try to recognize you, your what I mean to say balance and PIN number and etc. That is the power of the database. So behind the database, who is the main component? Try to access your data in a faster way, none other than indexing. In indexing, we are not going to look at the normal level index or a single level index. We are using the concept of multi-level indexing scheme that is called B trees and B plus trees. So the B trees and B plus trees are playing a very important role in real-time scenario, especially B plus. Nowadays, all your RDBMS, including Oracle or MySQL or Sybase, or you can say Microsoft SQL Server or PostgreSQL, any kind of RDBMS tools you take, they are following a B plus tree file organization. That means as a default that every DBMS has to follow B plus tree file organization because the way it able to store the data and the way it able to retrieve the data, that is the power of B plus tree. What is a B? What is a B? In that B plus tree and B trees, the B is nothing but it's completely different than your normal trees because the B trees and B plus trees are called balanced search trees. They are called as balanced search trees. They are not binary search trees. Please observe. They are not a binary search trees. They are balanced search trees. That means the tree is always balanced. That's why it is called as it's supposed to fill 50% of the tree. That is the today's agenda. What is the today's agenda? As the thumbnail of YouTube picture is showing that what is the minimum filling factor of any B plus tree or B tree? It is a 50%. Why 50%? Because the tree has to be balanced. As B implies, as it is a balanced search tree, it's not a binary search tree. So what is the difference between binary search tree and balanced search trees? Both are trees. Both are belongs to indexing concept only. But the power of balanced search trees than your B trees are completely, you can say, uncomparable. Those many advantages are there with B trees and B plus tree. Even in B tree also, why it is outdated, why we are choosing B plus tree, because the power of the B plus tree is a bit more advantageous than your B trees. So what is a B plus tree? What is a B tree? We are all waiting to learn it. Let's learn it. Before going into the discussion, our anthem is let's crack GATE and ESC with India's largest learning platform, none other than Unacademy. Get Plus subscription and access live and recorded lectures. About myself, Srinivasarao Sir, having 17 years of GATE experience in the subjects of DBMS, CN and operating system, also have good certifications in the respective areas. Throughout my journey of GATE, I taught in many BBM academies, including GATE Forum, made easy too with a high success rate. So use my referral code for any admission into Unacademy. Get the 10% off, either 12 months or 24 months subscription you can prefer. Let's crack Gate CSC. Subscribe to YouTube channel. Hit the bell icon. So let's start. What is a balanced search tree? The balanced search tree, as the name implies, that the tree is going to be balanced. That means you never find a concept of a skewing. You say that you're regular often to see skew concept in binary search trees, but you never have the concept of a skew here. There is no left skew, there is no right skew concept in balanced search tree, as a tree is balanced. That's why the name it implies as a balanced search trees. There are two famous balanced search trees. One is a B tree, the other one B plus tree, the other one B star tree. So what is the difference between each and the other? We will discuss in this lecture. I hope so. You're all ready to learn. Let's crack it. So what is the idea? What is the idea of a B tree and B plus tree? You say that by default they belongs to balanced search trees. And B tree and B plus tree is also called as multi-way tree, also called as, you can say, multi-level indexing. When you are talking about a multi-level indexing, it's not a single level index, it's a multi-level indexing. The B trees and B plus trees follows. What is the power of them? The power of them is that it is a completely constraint based. What is the constraint? The tree is always going to be the balanced. That assurance is going to be given by B trees and B plus trees. This is the power. And what is the necessity? What is the necessity to use these balanced search trees? The point number one. When you have a large database using a huge millions of records, then there is a requirement of B trees and B plus trees. It's not required for a small database which consists of 1000 and 2000 records. The B trees and B plus trees are mainly meant for a large database system. You can imagine Aadhaar database. You see in India, we are having 1 crore people, 100 crore people are having 10 thumb fingers. So how it able to retrieve your data? You imagine 100 crores into 10 fingers use database you may find especially in Aadhaar. But even just by typing or pressing your thumb, you able to retrieve your record in a quick manner because the work done behind is a B plus tree. Okay, friends. So why we are learning about a B plus tree? Because of this point. What is that? It get fast access of your data. And B plus trees are mainly meant for large database systems only. So why we are learning this balanced search trees? Because of this important point. What is that? There is a necessity called index. So in index, we have a concept called single level, and we have concept called multi-level. So when you talk a multi-level, there is a concept of B tree here, and there is a concept of indexed sequential access method, ISAM. Please observe, indexed sequential access method known as ISAM. Then what is the power of the B plus tree? The B plus tree has got the power of B tree and also has the features of your indexed sequential access methods. When you have these two combined together, it is the concept of B plus tree. So there is a concept of B tree and plus we have the concept of indexed sequential access methods. So why we are learning this B trees and B plus trees, as we are thinking that they all belongs to indexes. The important point is that when you talk about the index, when you talk about the index is nothing but you can simply say fast retrievals. We are all having indexes in your textbook, right? Your textbook has got data pages. Apart from data pages, your textbook also has index pages. You want to search any kind of a record, we are not going to search in data pages. First we go to the index and see that the particular word you are searching is available or not. If it available, then it gives you the page number. Just you go to the corresponding database number and get the data. That is the power of index, because index obviously follow a concept of binary search. So whenever you talk about the binary search concept, then we have the situation called log n base 2. Therefore, automatically your retrieval is completely comparing in the form of two powers, that is 2 power 0 and 2 power 1 and 2 power 2 and 2 power 3 and so on. Because index is following a binary search, the binary search is nothing but log n base 2 concept. So because of the fast retrieval, your database is going to maintain two types of records. One is purely data records, the other one purely index records. Index records are stored in index file, data records are stored in data file. Whenever you want to search the record, we are not going to search in data file. First, the preference goes to index file only. If the record is available, then it immediately get the data from the required page number. Otherwise, we will search in data file. But normally, whenever you search the record, the first preference goes to search your record only from index because it is taking the concept of binary search, that is log n base 2. But this is not at all a fit or sufficient in the nowadays database management system, because right now I want to give an example called YouTube. You want to see YouTube means several lakhs of videos are available. Several lakhs of videos are available, but how you able to tag the video? Just by searching a one keyword, it able to give you all the probabilities and the combinations, because they are following a concept of what? B plus tree. For every kind of fast retrieval of data, there is a requirement of B plus tree. It is not at all sufficient. Why? Because the B plus tree and B tree, they are following not log base 2n. They are following a what? Log n base m. This is the power. This is the searching capacity of your multi-level index known as either B tree or known as a B plus tree. So here, what is the meaning of n? N is nothing but a number of records. Number of index records. Here m is nothing but your searching capability, order of tree you can say. For example, this is your 2020 gate question. I am saying, for example, n is equal to something like 10 lakh records I have to find out a record. If I am saying individually I want to search, it is impossible. You need to search 10,000 times. That's why I am going for binary search. If I go for binary search, what will happen? I am going to put it in the form of, as the name implies binary, it is going to be in the form of log n base 2, because binary is nothing but two combination. Then how are you going to search? I am saying that a log 10 lakhs records, then I am using 2 power combination. It is taking a much more time to get your data. So in order to eliminate this problem, we have the concept. What is that concept? Log. If I am saying m is equal to, let us say I am saying m is equal to 10. So log base 10 of your 10 lakh records. See that how 5 times faster than your binary search, because I am saying that log base m. So you can increase or decrease. In binary search tree, you cannot increase or decrease the base value. But here I can able to increase your em value. Here m can be 1 or m can be 2 or m can be any number. It can able to up to n. That's why this is called dynamic. It's not a static. But binary search trees are what? Static trees, where your base value is always 2, but here base value can be dynamic. For example, I say that let m is equal to 10. You imagine how faster I could able to search the record. If I am saying that m is equal to 100, then what will happen? Log base 100, then you are having 10 lakh records. So here it is going to reduce your time search. Searching of your record is very faster in this case rather than 2 powers. So I have given three important things. One is that log base 2 of 10 lakh records. This is the one criteria I gave you, and other criteria I gave you here in this slide is nothing but log 100 base m and having 10 lakh records. So here what is going to happen? Your time complexity is increased here. Here your time complexity is decreased here, because the m is a dynamic. It can be increased as well as it can be decreased. Now we are all eagerly waiting how to represent this m value. and what is the 10 lakh and what is this M, how they are being represented, we will learn in this lecture. Now friends, observe carefully. I hope so you understand why we are learning about B trees and B plus trees. If anybody asks you, can you say about B plus tree? Simply you start with index, because B plus tree is an index which is a one category of index called multi-level index, where we are going to see the time complexity, or rather the time you are going to represent your record in the form of log base M and N. So this is, don't forget this. What is that? Log number of records with your M, where M is nothing but order of your tree, or you can also say that height of your tree, or you can also say that deep of your tree. That is the M. This M is not a static. It can be increased, it can be decreased. Decreased means time complexity will increase. Increased means time complexity will be decreased. Please understand. So come here. What is the next important point? The next important point, the first flavor, we are going to see a concept of B tree. So what is the B tree? First, let me tell you elaborately. You understand here, when I am talking M-way search tree, when I am talking M-way search tree, please observe friends. Here, M is nothing but order of tree only. Please observe carefully. Now, I am saying like this. If you are taking a binary search tree, tree grows vertically. Please observe carefully. Vertically, in the sense, I have 5 here, then I have 10 here, I have 4 here, then I have, please observe carefully, I have something like 9 here, I have something like 20 here. So your tree grows vertically because the maximum number of childs you can keep in binary search tree is only how many? 2. You cannot keep more than 2 in this. Every node can have at most 2 childs you can have in binary search tree. So I cannot able to place multiple number of nodes. Then what is going to happen? If your keys are increased, then height also is going to be proportionately increased, because you say that when I am talking about a binary, the binary stands for it is going to keep only maximum of 2 childs, not more than that. So therefore, what is going to happen? Your tree is going to be grown vertically. So when it is grown vertically, you please look at the situation like this. So this is how the tree is going to be retrieved, and see that how it is being represented. So in order to represent these number of keys, then what is going to happen? Your tree is going to be increased. When please observe carefully, when keys are increased, then tree height also will be increased. Then tree height also will be increased. Therefore, your time complexity is also going to increase to search the record. Please observe friends. That's why we are not going to follow binary search trees in real time. So in real time, we are going to prefer what? Multi-level indexing. So what is the concept of multi-level indexing? In multi-level indexing, we are going to see that index over index. Please observe. It is index over index. Now we observe carefully. Binary search tree also multi-level index only. I too agree. So multi-level indexing, when I am saying binary search tree will come, yes. But what is the problem with binary search tree? We have the concept of base 2. But in order to avoid this problem, we are taking a dynamic search tree with M. That is, M is nothing but order. So the M value can be increased or M value can be decreased. Therefore, we are having the concept here B tree and the concept of B plus tree. So what is the power of this? We are going to represent using a base m. Here m is nothing but your order of tree. What is the order of tree, friends? Order of tree is nothing but maximum number of child pointers. That is your m. So, what is the advantage than your binary search tree? Observe carefully. I am saying, for example, m is equal to 10. What is the meaning of this 10? You can have in a particular one node, how many? 10 pointers I can have. Please observe carefully. In a node, I can place 10 pointers and so on. And each pointer is representing one child at the down like this. Therefore, you see that you are having 10 child pointers. So when you are having a 10 child pointers here, then your tree is not grown vertically. Your tree grown what? Horizontally. Please observe. Here, the tree is going to grow horizontally, not vertically. Therefore, what is going to happen? Your height is automatically reduced. That is the power of B trees and B plus trees. Therefore, what will happen? Height is decreased. Therefore, your time complexity is also decreased because the tree is going to grow horizontally, not vertically, because it all depends on that your m value. Now, you observe one more important point, friends. If I am saying m is equal to 5, you observe carefully. Therefore, you take a one node, you can have 5 child pointers. Please observe carefully. So when I am saying m is equal to 5, maximum of 5 child pointers, nothing but leaf pointers, nothing but block pointers. This is representing one block, this is representing another 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 block. Now you observe this child also can have 5 pointers. Please observe, friends, carefully. And this child also can have 5 pointers. 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 See, look at the down. Look at the down. This is a further has 5 pointers. This is a further has 5 pointers. This is a further has 5 pointers. And this is a further has 5 pointers. Again, you can have a down like this. What is the meaning of that? Every block is ready to store 4 keys. I say key 1, 2, 3, 4. I say next 5, 6, 7, 8 and 9, 10, 11, 12. See that how many keys I can able to position it here. But whereas in binary search tree, you cannot position it these many. See, in the second level itself, I could able to manage how many blocks? 1, 2, 3, 4, 5. In binary search tree, in second level, you can able to manage only what? 2 childs only. But here, I could able to manage how many? Childs, 5 childs, and each 5 child has a 5 pointers inside. That means the tree grown like anything horizontally, and sometimes it comes into vertically whenever all blocks are filled. Instead of if I am saying this 5, I say 20. You imagine that you have a 20 pointers in the first blade and 20 childs you have got in the next level. So this is the concept of the idea of your multi-level indexing, especially B trees and B plus trees. So if I'm saying m is equal to 20, you imagine I have 20 child pointers from your root. Therefore, what happened? This has got 20 pointers here. This has got 20 pointers here. This has got 20 pointers here. So T grows like this. It all depends upon your m value. Now you're all having how to calculate m value. Okay. So when m is equal to 10 is nothing but you can have 9 keys at any time. When m is equal to 20 is nothing but you can have n minus 1 keys. So m I given in the sense it is nothing but maximum number of child pointers, and maximum number of keys are nothing but m minus 1. Please remember that. So come to the next point. What is the next point? So common factor we learned in B tree and B plus tree. The common factors are both are depends on m value, and both are having searching capability log m base n, and both are having a common property that horizontal growth, and next one that the both are having a common property that m can be increased or m can be decreased. Please observe carefully. And these are the common points. And one more point is that both trees are balanced. They are balanced search trees only. Observe carefully. Because of the balanced search trees, maximum filling, maximum filling is M, and minimum filling, that is today's our agenda in our today's class. The minimum filling, how much I said? This M is nothing but complete full. This is a complete full. I have filled completely with M. And what is the minimum filling? The minimum filling is exactly you supposed to do how much, friends? 50% filling. If you, that is a mandatory that your tree is supposed to be what? Half full. What is the meaning of half full? You need to maintain a 50% of the key fillings. And this is called as a complete full. 100%. This is called as half full because it is filled at 50%. So if a tree is filled, please observe. If tree is filled 60% above, then it is the concept of what? B star tree. Okay, friends, it is in between complete full as well as half full. When I am saying complete full, so M. When I am saying half full, it is M by 2 you supposed to maintain. So how to maintain them, we will see now. So what is the concept of a B tree? When you have a B tree, so we know that it starts with a root node, and it can have up to m child pointers, and it can grow like the down the ladder. Now see that you can have n children pointers, and you can have n minus 1 number of keys. The structure of leaf node is very similar to structure of root and internal node. And what are its disadvantages? This is a major drawback. So duplicate keys are not allowed in B tree, and duplicate keys are allowed in B plus tree. So in B plus tree, this is going to be the drawback. In B plus tree, this is going to be the positive side. And what are the drawbacks for B tree? The drawbacks for B tree is nothing but record pointers are available at every level of the tree. So in order to reduce them, you're supposed to use the B plus tree. So what is the difference between B tree and B plus tree? If anybody asks you, simple answer you can give. What is the difference between B tree and B plus tree? Everything is same, all are same. Only one is the difference. What is that? No dupes. And here dupes are allowed. Point number 1. Point number 2, here that record pointers are available. Record pointers are available at every level. At every level of tree. But in B plus tree, record pointers are available only at leaf node. Record pointers are available only at leaf node. These are the two differences between your B trees and B plus trees. Remaining all are same. So let me explain what is the concept of a B tree and how the B tree can be implemented. As far as our gate and any kind of examination concern, we need to learn its representation only. Yeah. Now you observe what is the B tree. Three important points I will tell you about B tree. Number one, tree starts with root. Number two, observe carefully friends. Root can have maximum of m child pointers. Yeah, please wait all of you. What is a child pointer? What is a record pointer? I will tell you. Please give me time. Because we are going to represent now B tree. You will understand after 5 minutes. So root can have maximum of m child pointers and minimum of, you need to satisfy binary search tree here, minimum of 2 child pointers. Please observe friends. Number 3, I have a question to all of you, those who are online. Please, all of you, again I am repeating, I have a question to all the audience who are on live, that what is the minimum representation in your binary search tree? How many minimum child pointers you can maintain? How many maximum child pointers you can maintain in binary search tree? Please comment through chat. Minimum child pointers and the maximum child pointers of your binary search tree. Please type comment. Next one. Internal node can have maximum of m child pointers and minimum of ceil of m by 2. Ceil of m by 2 block pointers. This is the point number 3. Please observe. Tree starts with the root. Root can have maximum of m block pointers. Block pointers, child pointers, leaf pointers, all are same, which is going to represent into the next block. And the minimum you supposed to maintain 2 child pointers. And you observe carefully, internal node can have maximum of m block pointers, child pointers or leaf pointers, and minimum you supposed to have m by 2 block pointers. And next you observe the fourth point is leaf. Leaf node is the last node. Please observe, leaf node is nothing but last node. Leaf node may have maximum of m minus 1 keys and a minimum of, please observe friends, ceil of m by 2 minus 1 keys. And the last point, structure of leaf node is the same as root or internal node. These are the 5 points you need to remember while writing the narration for B tree. So 5 points I said. Please once again let us repeat the 5 points. Tree starts with the root node. Point number 1. Root can have m block pointers. Minimum supposed to have 2 block pointers as far as root concerned. These are for root and this is for your middle node. Internal node can have maximum of m block pointers, but minimum you supposed to maintain, this is only half full. And when I'm saying m, it is nothing but complete full. So minimum you supposed to maintain half m by 2. And as far as the leaf node concern, if you concentrate, so maximum you can have m minus 1 keys and minimum you can have ceil of m by 2 minus 1. So Ceil is nothing but upper value we will take if at all you get the m by 2 is in a fraction. And the last point is that the structure of the block structure of leaf is very similar to block structure of root and internal node. Okay, now I am giving you a diagram representation. Please observe carefully. I am saying construct binary search tree of 5, 2, 3, 15, 20, 25, 1. These are your keys. So I'm constructing starts with 5. I'm constructing binary search tree, friends. You all know how to construct it. And 2 here, and 3 here, 15 here, 20 here, 25 here, 1 here. So after construction of binary search tree, you observe number of levels is equal to, you can type from comment, and what is the height of the tree? Please tell me what are the number of levels and what is the height of the tree. So height of the tree, you can say how much it is. Height of the tree, how much you can say. Height of the tree, number of levels are 4. Height of the tree, please respond from comment. Height of the tree, what is height of the tree? Yeah, height of the tree is a 4. So height of the tree is nothing but number of levels minus 1, that is nothing but 3. Your number of levels are 4. This is a level, and this is the next level, this is the next level, and this is the next level. And you observe carefully that there is a what? A skew. So the above tree has skew. What is a skew? Because tree is not balanced. It is going like this. The tree is not balanced. We don't have key here, we don't have a key here, we don't have a key here. These are the main drawbacks of your binary search tree. So in order to avoid these problems, now I'm constructing B tree. The construction is only the difference between B tree and B plus tree. Today I'm going to present the way the B tree and B plus trees are constructed. By knowing the construction, you understand the narration formula of a B tree as well as B plus tree. Nothing to by heart. Please observe the same keys. I'm going to construct a B tree now. Now let me construct B tree. B tree with the same keys 5, 2, 3, 15, 20, 25. 15, 20, 25, 1. Okay. Now, in order to construct B tree, you're supposed to tell what is the M value. Please understand, if I am saying that M is equal to 2, then this is very similar to, once again, binary search tree. Please observe, friends. So I supposed to take more than that. So I'm taking it's completely depends on M only. If I'm saying let M is equal to, I say 5. What is the meaning of 5? 5 leaf pointers or block pointers or child pointers. That means you take a one big node. This block can consist a maximum of 5 pointers. It can point to 5 nodes other side. 5 nodes, the leaf nodes, it can point like this. 1, 2, 3, 4, 5 nodes. So these pointers are called leaf pointers, which are pointing to next level. Leaf pointers, also called as block pointers, which are pointing to next level blocks, also called as what? Tree pointers. Okay, now I can able to keep some values. So as I am saying M is equal to 5, then I can have a maximum number of keys I can have. Please observe, maximum keys are nothing but minus 1 to that, that is m minus 1. So give 5 keys from your top. So at a time, I am in a position to insert 4 keys at a time. That is the power of B trees and B plus tree. And these keys are ascending every time. Every time they are going to perform ascending order. This is one of the problem with that. So every time it is going to reshuffle the keys. So 5 to 13, 5 to 3 and 15, I am inserting here. First 2 will come and its record pointer, and 3 will come, its record pointer, 5 will come, its record pointer, 15 will come, its record pointer. What is a record pointer? Hold for some time. I have inserted successfully at a time how many? 4 keys, because my M is a 5, I can initiate 4 keys at a time and 5 block pointers I can have. When M is a 5, you can have a maximum filling up to M minus 1 keys. Okay friends, now we want to insert 20. When I am inserting, this is your level 0 or level 1, whatever it may be. Now if I am saying insert next element, that is 20 into this. When I am inserting 20 into that, what will happen? Your tree is going to be expanded like this: 2 dot, 3 dot, 5 dot, 15 dot, 20 dot. Okay, this is how the tree is expanded, but is invalid. This is why this is invalid. Your maximum child pointers are how many? Only 5. And you can keep how many keys? Maximum only 4 keys. But here you got how many keys? 5 keys. Because you got 5 keys, then your block pointers are increased to your 5 to 6. Therefore, this is greater than to your M, which is invalid. So whenever it is greater than to M, which is invalid, then you start to apply the concept of a what? Split of a node. Now you will see a concept of a what? Splitting concept. So now exactly the tree will be divided into 2 halves. That's the meaning of split. The middle node will be represented as a node, and left and right you will find it. Therefore, your tree is going to be divided into 2 halves. That is nothing but M by 2. Therefore, what will happen? Now I am splitting that node. So splitting is a special rule in balanced search trees. So splitting. What is the splitting rule? You can say middle, or you can also say like this. What is that? Seal of M by 2 order you can take. So already your tree is grown like this, which consists of the following keys: 2, 3, 5, 15, 20. 2, 3, 5, 15 and 20, which is divided into exactly 2 halves. This goes to the middle. So therefore, your 5 will be your root. Observe friends, your 5 will be your root, and there is a record pointer, and I can have on this particular node, please observe carefully, the node capacity I can grow up to M. Your M is equal to 5, so I am taking 5 block pointers like this. Okay, so 1 and 2 and 3 and 4 and 5, I don't have keys in that, just I am giving as a nulls only, as there are no keys with me. Now it is a left tree and a right tree. Your left tree is what? 2 dot 3 dot, and still I can have accommodation. I can go up to 4 keys in this node also, please observe. So this is 1, and this is another pointer, and this is another pointer. I don't have key right now, and this is another pointer. I don't have key right now, and close it. So I can have 5 pointers here also, as M is equal to 5. Observe, this is applicable to entire tree. And here also I have same position, that is 15 and record pointer, 20 and record pointer, and once again you can have other pointer, you can have other pointer, and where they are with nulls, as your m is equal to 5 to be applied, and this is separated and this is separated. Okay friends, now we want to apply the next key, that's what, 25 and 1. So I can insert 25. So insert 25. By inserting 25, you observe like this. So 25 greater than 2, please observe like this. 25, please observe. 25 is greater than 2, greater than 3, greater than 5, greater than 15, greater than 20. So I have space here. So I can able to keep 25 here. No problem at all. What is the next key? 1 only. So 1 can be inserted here. I am saying that insert 1. So 1 is less than 2 and that can be placed here. Therefore, finally, you will get 1, 2, 3 and null here. You will get 15 dot, 20 dot, 25 dot, no problem. So here you are having a 1, 2, 3 dot and still you have accommodation one more key. As there are no keys with me, I can stop the process. Okay. Now you observe, this is how your B tree is represented with this root. Okay friends. So this complete structure is index for you. This is not a data file. It is a what? Index file which has got 2 levels. Please observe, which has got 2 levels. This is your level 1 and this is your level 2. So what is your height? Your height is only 1. Number of levels 2. Height is only 1. But earlier BST you observe carefully. The number of levels are 4. The height is 3. Here height is 0 and number of levels are 2. You can say that as number of levels are 2, your height is 1. So this completely I am talking about from here to here. It's a completely what? Index. It's not a data file. It is your index file only. Now how it can link to your data file, that is very, very important. So I will redraw the structure in the next page. Observe carefully. So at the top we have 5. So at the top we have 5. So remaining can be nulls to you, no problem. And the left side I have, so record pointer, please I'm changing the color of the point. This is record pointer and you have here few keys 1 and 2 and 3 and you have record pointers over there. What is record pointer? You all will understand now. And this side you have, what is that? 15, 20, 25. So take a block here, 15 here, 20 here, 25 here. Now observe friends, it is also having record pointers. Now you see, this completely I am calling as a multi-level index. Now I have a data file here. And I said that your tree is perfectly in a sorting order. 1, 2, 3, 5, 15, 20, 25. Almost all it is in ascending order only. Your data file has the following records. These are your data records. Observe. Your data records exactly will be in your index order only. 1, 2, 3, 5, 15, 20 and 25. This is your, you can say, data file, and this you can say as your index file. Now this record pointer get the data from data file. This record pointer get the data from data file. This record pointer get the data from data file. This record pointer get the record. This also get the record. This pointer is get the record. This pointer is get the record. So the record pointer use is nothing but it point to original record to pull the data like a page number. So if I find something in your index page, for example, a property called atomicity, you go to the index and see that atomicity is available. It will give you 756 page number and use that page number, go to the corresponding page number. So the data pointer works like your page number only. So therefore, this pointer will give you the direction to your particular record. What is the use of this key? Now I will tell you. What is the use of this key? This key is nothing but searching criteria, also called as search key only. For example, you open MS Word document. Please listen, all of you. Real time analogy I am giving you. You open MS Word document which consists of 100 pages. I want to search information hello. So if I am searching line by line, hello, line by line, line by line, line by line, in all the 100 pages, it takes a lot of time. So what do we do simply? We go for search, dynamic search. Control F, if you type, then it will give you find. So in that find, please observe. When you ask find option in any kind of a document, it will ask you one box. This box, what you need to type? Please tell me, friends. What you need to type in that box? This one, search key only. If I am saying hello, then it starts searching line by line and page by page. Once the page is completed, it goes to the next page. Next page is nothing but your block pointer only. Please observe. If this is not available here, then it goes to the next block. If not available, it goes to the next block. This is your page number 1, and this is your page number 2, and this is your page number 3. So these are called blocks, and that's the use of block pointers. Nothing but pages only. And what are they? Line numbers. Line 1, line 2, line 3, line 4. If you are able to get it, immediately that particular record is going to be retrieved. Nothing but tracks. Blocks are nothing but tracks, and taking the book is nothing but exact record only. Therefore, when you type your search key here, then this hello is going to spread over in the entire document and try to verify whether hello is available or not. So for example, in the same story, if I am saying that I want to search 20, this is your search key now. If I am asking you to search your 20, it starts checking 20 is greater than 5 and greater than 15. Yes, I got 20 here. In block 3, I got 23, and you cannot get directly record. Take its associate to record pointer. With the help of pointer only you can able to pull the information. That's why there is a requirement of, in order to pull your data, there is a requirement of what? See, n plus 1 blocks. N plus 1 blocks required to pull your data. Why n plus 1 blocks? Please observe carefully. So I have searched the record in this particular file and use the record pointer. Go to another block. The data file is a different block. Please observe. This data file is a different block. Therefore now your database has got 4 blocks. 3 blocks I am using for index. 1 block I am using for data. Altogether 4 blocks I am maintaining for the entire database management system. So this is the representation of your B tree. Okay, friends. So here key is nothing but, please observe, here key is nothing but the searching element. The key is nothing but searching element. For example, you see, you go to bank and ask that what is my balance available in my account. What he will ask you, banker will ask you. What banker will ask you? I stand in front of a counter and I ask the counter person that what is my account balance. What he will ask, what the banker will ask you. Please, anybody can respond from comment. What banker will ask you? All of you. What banker will ask you? Yes, account number. So you need to give that account number. The giving of account number is nothing but what? Your search key only. With what I need to search. With what I need to search. So he will type that account number in the box. He will also get text box. By typing account number, it traces out in the index file first. In index file, it traces out. It checks that whether that account number is there or not. It never touches the data file. Again, I am repeating. It never checks with the data file. It only checks with index file only. If available, it will show. Otherwise, it will say that our account number does not exist. Please remember that. So they are not going to search from the database data file. They are going to search from index file only. If it available, 100% your record will available. Otherwise, your record does not exist. Therefore, the account number is your key here. So I am taking like 1, 2, 3, 5, 15, 20, 25. In real time, you can take account number, driving license number, mobile number, PAN account number, or Aadhaar number, any kind of numbers, all are indexed files only nowadays. You please observe, friends. All are indexed files. And one more, barcode. Nowadays, we are all very much aware of with barcode. Barcode is nothing but one index file only. If you just show your barcode, then machine is going to convert into a key. A key is nothing but your search key only. Clear? So now, what do you find in this structure? You observe carefully. What do you find in this structure? See, this is your leaf. Block 2 and block 3 is your leaf, because the leaf is ahead your to data file which is trying to get your data. Please observe. So I am writing here. What is that? Block 1 is your root. Block 1 is our root node. This is also called as a root block, which is diverting to different shelves or blocks. And block 2 and block 3 are leaf nodes. Now I said the very important point. This is the major quotation of your B tree. What is that? Leaf node structure is equal to root and internal node structure. Leaf node structure equal to root and internal node structure. Except what? Except leaf do not have blocks. Except block pointers are nulls. Except block pointers are nulls. So I will show you. Observe carefully. I am keeping in different color. Please see. This is my block pointer. 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 Here also block pointers are there. See, the block pointers are nothing. They are not directing to anybody. They are simply what? Nulls only. As they could not able to divert to next level blocks. That is only last level to you. Therefore, block pointers are nulls. Remaining everything is same to your root and internal node structure. Except root and internal node has a chaining to the next level, but leaf node do not have chaining to the next level. It stops the process there because that is only your end of the level. Clear? So come to the next point. So please observe carefully. Your block 1 is a root node. Block 2 and block 3 are nothing but leaf nodes. And the difference, the B tree is main is that leaf node structure is equal to root and internal node structure, except tree pointers are nulls. So come to the point. This is your previous tree. 5 is the root. And here we have a record pointer. And you have left and right hand block pointers. You have 1, 2 and 3. You have 15, 20, 25. And the entire concept I am calling it as index. Now you see every block of B tree has the following elements. What are the elements you are able to see? Observe. Every block I am keeping. This is your block 1 and this is your block 2. This is in block 3. What are the elements you are finding? Common elements. Every block has got what? Please observe. Block pointers. And what else? key. Here also you have block pointers. Please observe. Every block has block pointers. This is one of the common element to all the blocks. And the next element is key. Everywhere you are finding a keys, and everywhere you are finding a what? Record pointers. Please observe. Record pointers plays a very important role to pull the data from your original data file. So record pointers. I have a question to all of you. What is the question? Maximum how many block pointers a node can have? Maximum. I am telling about a maximum. Maximum how many record pointers a node can have? Maximum. Nothing but m block pointers. How many keys maximum I can have? m minus 1 keys. And the maximum record pointers, how many we have? As many keys, those many record pointers. These are all available in one particular block. Therefore, what is your structure? N block pointers. What is your structure? M block pointers plus m minus 1 keys, maximum I am talking, plus m minus 1 record pointers, all are placed in block only. This is the formula. This is the formula for regarding what? M value. So using that, I can find the order of your M. Please observe. Using this, I can find the order of the M. M is nothing but how many record pointers you can have in your block, that you will get. So that is the equation of your B tree. Please remember, very easy to solve. What is that? M block pointers, M minus 1 keys, M record pointers are available in every level of the block of your index. Therefore, if I ask you a question like this, please observe. I am asking a question. Block pointer is equal to 6 bytes. He will give all this in exam. And record pointer is equal to 7 bytes. Key field is equal to 9 bytes. Key field is equal to 9 bytes. And block size is equal to 512 bytes. Now you observe, he is asking find order or degree of B tree. I can use the equation. What is the equation, friends? Please, you also can recollect the equation. Let's crack it. What is that? M block pointers plus M minus 1 keys plus M minus 1 record pointers equal to your block size. All are given. What are given? Block pointer 6 bytes, M 6 bytes plus M minus 1. Key value is given. What is the key value? 9 bytes. It takes 9 bytes to store your key. Record pointer M minus 1 record pointer, I suppose to see here it is given 7 bytes, and your block size is given a 512 bytes. All are in bytes format only, no need of conversion into bits. Directly I can cancel all your by. So you take only numerical M6, then 9M minus 9 plus 7M minus 7 is equal to 512. Therefore, what is your M? M6, 9, that is 15 plus 7, 22M. So finally we got 22M is equal to 512 plus 9 minus 519, and this is a 9, 528. Therefore, your M is equal to 528 by 22. That's all, friends. So M6 plus 9M plus 7M, it is a 16 plus 6, it is a 22M is equal to 528 by 22. Almost all you may get around 22 23. Around you will get 23. What is the meaning of the 23? Observe carefully. If I am saying that, if I am saying that let m is equal to 23, what is the meaning of 23? Now you can imagine, all of you, please observe carefully. Maximum filling I am writing. What is the maximum filling? Level, nodes, and block pointers, keys, and block pointers. Observe now, level 1. Observe now, all of you. Level 1. Level 1. How many nodes you can have? Level 1. How many nodes you can have? Only one node starts with the root. Observe carefully. Only one node start with the root. So now you tell me maximum how many keys you can able to keep? Maximum how many block pointers you can able to keep? Like 24. How many keys you can able to keep? 23. Level 2. Please observe. These 24 block pointers will be those many nodes to you. And you got 24 square. You got 24 into 23 keys. Level 3. 24 square your nodes. Then you will get 24 cube. And you will get 24 square into every node you are going to store 23 keys. So you observe carefully, friends. So whatever it may be, either 24 or 23, this is the concept. What is the concept? Please observe carefully. At level 3, you imagine these many keys I can able to produce. The tree grown horizontally, very, very big tree. 24 square into 23, you imagine huge number of records you can able to store exactly at level 3. That is the power of your B tree. If level 3, how many keys in binary search tree? Please observe. Binary search tree, dash keys for level 3. You can say it's nothing but 2 power 3 minus 1. I can have 7 keys at max. You cannot have more than that. But see, imagine by taking m is equal to 23, I can spread over the complete tree up to 24 square into 24 3. This is the concept. This is the concept of your B trees. Why it is a dynamic, why it is being real time used, how the tree is grown horizontally. Okay, friends? So observe this. So this is the equation. What is the equation? Number of block pointers and n minus 1 keys, n minus 1 record pointers, they are into block. This is your maximum filling. This is very, very important. Very, very important. This is your maximum filling. What is that? So level 1, one node only I have. I can store p block pointers and you can have p minus 1 keys. Level 2, these p block pointers are your next level nodes. Like I'm talking like this. Every block pointer is a node to you. Please observe. Every block pointer is a node to you at the next level. Every block pointer is a node to you at the next level. And you have this and to these many block pointers. That is a p square block pointers. And how many keys I can keep? P minus 1 keys in a p blocks. And the next level, these are going to be your p square nodes. And you have block pointers a p cube and p minus 1 keys in a p square. Okay, friends? Now you observe carefully. Next one point I will tell you. Level is equal to 3. Number of levels equal to 3. This is a very, very important question. Order is equal to 5. Dash keys at max. Totally in B tree. The answer is simple. What is that? Anybody? Number of levels 3. So I can say that m power l minus 1. Your m is nothing but 5. Number of levels 3 minus 1. That is equal to 124 keys exactly. If I am taking your binary search tree, it's nothing but 2 power 3 minus 1, that is equal to 7 keys. This is the difference. This is the difference between your B tree and binary search tree. Okay, friends? So, you want to know why this 124 keys came? You would like to know? Please look at why 124 keys came. Why 124 keys? Because level 1, one node, how many block pointers? M block pointers. How many keys? M minus 1 keys. Here your M is nothing but 5 and 4 keys. And level 2, these 5 are belongs to your block pointers 5 nodes, and you have 5 square pointers. You have 5 nodes and each node can store 4 keys. And level 3, you have 5 square pointers, 5 square nodes, 5 cube block pointers, 5 square into 4. Total altogether 124 keys. This is 4 and this is 5 fours are 20. This is how much it is? 25 into 4. It is 100. Total you got 124 keys. Okay friends, all of you, is it clear? All of you, why this has been given 124 keys using a formula, and the same you can also interpret using a tablet format. Clear? It's a very simple. What is that? I can say very simply that what is your order and say that what are your levels and keep minus 1. This is only your answer. Okay. This is which I have told you is complete full. Please understand. Complete full means I am using 100% filling I am doing. When you are doing 100% filling, 100% filling when you are doing, it says completely full. Understand? But I need to maintain half full also. That's very, very important. That's why B tree and B plus tree is supposed to maintain balanced. The balance is nothing but what? Half full. What is your half full? Please look at. This is your half full. This is your half full. Half full is nothing but 50% of filling you supposed to do. 50% of filling to do. That is the meaning of half full. As you want to say that you are going for balanced search trees. As you are going for balanced search trees, you are supposed to follow minimum half full. What is a minimum half full, friends? Please see. Minimum root minimum. Please tell me. Root minimum 2 pointers you need to maintain. Internal node you're supposed to maintain m by 2. M is nothing but order. And leaf node is supposed to maintain m by 2 minus 1 keys. These points are already given earlier. The same is there here only. So level 1 minimum 2 pointers. Please, an internal node minimum m by 2 pointers and keys m by 2 minus 1. Again m by 2 square, m by 2 into m by 2 minus 1. You need to maintain a minimum like this. Otherwise it's not a B tree or B plus tree. The minimum is supposed to maintain half full. If you able to full more than 50 and lesser than 100, it is a B star tree. Very simple. If you able to fill more than 50 towards 200, it is a B star tree. Everybody clear? Please observe carefully. What is that? M is equal to something like, I say 6. What is the half full? Please see. Your half full is a 6. Sorry. Your half full is a 6 by 2. Complete full is your 6. This is m by 2 seal off. This is m. Clear, friends? So you need to maintain a tree. Minimum you need to maintain a tree everywhere. Please understand. Everywhere. Minimum how many pointers you need to maintain? 3 block pointers you need to maintain. Please observe. You need to maintain a minimum 3 block pointers as your m is equal to 6. So everywhere in every node you need to maintain 3 block pointers and minimum 2 keys. Observe carefully. So therefore, in next node, you will get 3 nodes. This node also supposed to maintain 3 block pointers. This node also supposed to maintain 3 block pointers. This node also supposed to maintain 3 block pointers. Observe carefully. So again you go to the next level. You will get one more node which also maintain 3 block pointers. This also has to maintain 3 block pointers. This also has to maintain 3 block pointers. Please observe, friends. This also has to maintain 3 block pointers, and this and this and this and this and this. Now my question is dash minimum keys. When m is equal to 6, you need to answer. Total dash number of minimum keys when m is equal to 6 and level is equal to 3. Observe carefully, friends. This is a level 1, this is a level 2, and this is a level 3. I am asking total number of keys when m is equal to 6 and the number of levels are 3. What is your answer? You can say K1, K2, 3, 4, 5, 6, 7, 8, and this is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is how you can able to represent like this. What is that? You're supposed to maintain two keys. That means this level you maintain 2 keys here. Please observe. This level you maintain 1, 2, 3. 3 into 2. It is a 6 keys here. And this is 1, 2, 3, 4, 5. And we have got how many blocks here? 3 blocks here. And 3 blocks here. 3 blocks here. So every block is supposed to maintain two keys like this. So 2 keys here, 2 keys here, 2 keys here, 2 keys here. Here also supposed to maintain 2 keys here. Here also is supposed to maintain 2 keys here. Here also is supposed to maintain 2 keys here. Therefore, your answer is like this. Please observe, friends. Yes, you're right now. Your answer is like this. Please observe. Don't worry. I'm giving you the solution. Maximum number of keys in a B tree with order P, it's nothing but number of keys is equal to, I already said, m of L minus 1. Minimum keys representation is like this. Please observe. I say, what is that? 1 plus 2 into m by 2. Please observe. L minus 1 minus 1. Oh, your m is already we produced. What is your m? Your m is 6, L is equal to 3. So it is nothing but, therefore I can write like this. 1 plus 2, 6 by 2, 3 minus 1. It's nothing but 17 keys. Why 17 keys? Please observe here. Why 17 keys? You can calculate why we have got 17 keys. Anybody? Why we have got 17 keys? So you're all thinking that it is 18 keys, but there is a small issue. What is the issue? You please look at once our previous slide. What is our previous slide? All of you, please listen carefully. At root, please observe. At root, minimum nodes how many? 1. At root, minimum nodes how many? 1. Minimum keys how many? 1. Minimum pointers how many? 2. Therefore, what will happen? Now you observe carefully. I got a 1 node which consists of two pointers. I supposed to give only one key. Now this internal node is supposed to maintain three block pointers. Now this has to maintain three block pointers. Please observe now. Now therefore this has to maintain three block pointers. Now this has to maintain three block pointers. Now this has to maintain three block pointers. Observe friends. That means two keys you need to keep. Two keys. Here also two keys. Here two keys. Here one key. And this also require three block pointers and two keys. This also require three pointers, two keys. This also require three pointers, two keys. So almost all it is 17 keys. Because please observe carefully, our root has to start with a one node, with a one key, with the two block pointers. When there are two pointers, you're supposed to have only the one key only. Okay, friends. But what is the problem? The problem is, what is the problem with B tree? B tree problem. Only one. What is the B tree problem? Leaf point, that is record pointers are existed at all the levels of the tree. Record pointers are existed at all levels of tree. This is the major drawback. Therefore, complexity structure. Complexity structure. Yes. No. Please observe carefully. Please observe carefully, all of you. In B trees, you do not find any kind of duplicates. Please observe friends carefully. In B tree, you do not find any kind of duplicates. Duplicates only you will find in a B plus tree. This is the one of the positive of B tree. See, in this structure you never find any duplicates. It's a unique structure, but only one problem. What is that? Record pointers are existed at all the level of tree. So please look at the screen carefully. Look at the screen carefully. One, I want to search one. One is available in block 2. Agreed? I want to search 2. 2 is available in block 2 only. I want to search 3. 3 is available in block 2 only. I want to search 5. I want to search 5. Where are you going to bring? You need to contact root. Understand? You need to also touch root in order to get your record. This is the major point. So everywhere you have the concept of what record pointers in all the trees. This is a major drawback. You need to go to the root and internal node to pull the record. This is a major problem with your B tree structure. So this problem is eliminated in B plus tree structure. Say that the leaf nodes record pointers are only available at leaf nodes only. This is the one of the greatest point of your B plus tree. What is that? Please observe. Observe the B plus tree conditions. What is the B plus tree condition? You see that few important things. A B plus tree is always balanced. We agreed. And it's supposed to be half full. That is n by 2. No problem. Minimum you have to fill 50%. No problem. This is a very important point. What is that? All data is stored in the leaf node only. Therefore, record pointers are available only at the leaf, not at the internal node and the record root blocks. Record pointers or data pointers or index pointers are exactly available only in the leaf. We never contact the upward of your root structure. We don't mind about internal node. We don't mind about root node. We will touch only leaf node only. This is the point. Therefore, we see that record pointers are available only at the leaves. Okay. Now, let me specify what is that. Record pointers are available only in leaf node. Therefore, the structure of leaf node, different from structure of internal node and root node. Structure of internal node and root node. Root node and internal node structure is same, but leaf node is different. And therefore, please observe, leaf need separate M value, and root and internal node need separate M value. Root and internal node has separate M value because two structures, 2 degrees. Two structures, 2 degrees. Let me do. The earlier question is 2, 3, 5, 15, 25, 1. Now he is asking you to construct. This is our last point, friends. I will show you how the B plus tree will be constructed and close the session. And the evening special class, we will discuss the problems. How can you answer the problems? So construction of B tree requires two important things. One thing is leaf order. This is very, very important. I can say M2. And other order is also required. That is root and internal order. That is M1. In B tree, only one order. It's all for every blocks, including leaf blocks. But in B plus tree, you need two orders. One is for leaf, one is for root order. I will show you. Don't be panic. We'll understand the structure. Don't worry. Observe carefully. So here this M2 is nothing but maximum number of keys allowed. Maximum number of keys allowed in leaf node is observed. And this M1 is as usually, what is that? Maximum number of block pointer. This is a common there and here. In B tree and B plus tree, this is common. Common structure, B tree and B plus tree having this block pointers and keys only. This is the common. Okay. So you can find maximum number of keys in root and internal node is M1 minus 1. Here M1 is nothing but root order. And here directly I can position it. Maximum number of keys directly allowed. How much? It's not M minus 1. It's directly what? M2 only. So leaf order means you can accommodate all the keys. Root order means M minus 1 keys only you can accommodate. And M block pointers you can accommodate. Okay. Now I will construct this. I am saying let M2 is equal to 2. This M2 I am calling it as P leaf, order for leaf, and M1 I am saying 3, which is nothing but order for root. So I have taken two orders as two orders are required for B plus tree. One is a leaf order, that is a P leaf 2. One is a root order, that is nothing but 3. Here 2 is nothing but maximum keys you can accommodate. Here 3 is nothing but maximum block pointers you can accommodate. Everybody is clear so far? Just I will show you the now construction process. So point number 1, tree starts with, please observe friends, leaf. Please see, tree starts with leaf. Now I said that your P leaf is equal to 2. So I can accommodate two keys. What are the keys you want to insert? 2 and 3. Keys will be always in ascending order only. That is the same principles we have there and here. Keys will be every time very sorted. So P leaf is equal to 2. Therefore, I can accommodate here two keys. What are two keys? 2, 3, record pointer and record pointer. Please observe, friends. This is your leaf block. Now I want to insert 5. When you insert 5 into this, you know what will happen. 2 dot, 3 dot, 5 dot. Okay. Now this is your leaf is extending like this. And I say that this is greater than your P leaf. Because you have mentioned 3 keys, it's greater than to your 2 keys. Therefore, what is required? The leaf is splitting. So middle goes to root. Middle goes to root. Now therefore, this 3 will come into root. Now the root node can have block pointers. Please observe. Root node can have block pointers as usually. So block pointer, as there is a one key, two block pointers are there. Left side positioning, right side positioning. This is the crucial task. What is the crucial task? Whether you are doing a splitting, I do splitting, whether you want to use left bias or right bias, or leftmost split or rightmost split. Leftmost split is less than is equal to you need to sustain. Rightmost split is greater than is equal to you need to sustain. I am taking leftmost split. In exam you will say, otherwise you consider which split you want. Either split you can take. I am taking a left biasing only. Therefore, what will happen? It is a 3 at the root. As a one key, there are 2 pointers. I am taking left splitting assumption. Left splitting I am doing. What is left splitting? You need to maintain lesser than is equal to. What is the meaning of less than is equal to? 2 dot, 3 dot. You need to maintain. And the rest of the value. What is the rest of the value? Please observe. 2 dot, 3 dot. This will come into left side. This greatest value goes into other side. So therefore 5 will be this side. And this is your leaf. This is your leaf node. And this is also your leaf node. And this is your root node. I said along with your key, record pointers are mentioned. Don't forget that. Along with your key, record pointers are mentioned. Record pointers are mentioned only at leaf nodes only. Clear? Now let us insert. What is the next key? 15, 25, 1. So insert 15. So 15 is greater than 2, greater than 3, and greater than 5. I am checking like this. And come here finally. 15 is greater than 5. I can accommodate here. Why? Because there is a room. Because your P leaf is equal to how many? 2. Your P root is equal to 3. 3 block pointers. There are 2 block pointers. 2 keys I can accommodate. Already one is present. The second one I am inserting. Therefore, 3 here. And this side 2 dot, 3 dot. This side 5 dot, 15 dot. It's a fine. Now, I want to insert, please observe. I want to insert 25 now. So when you are inserting 25, it's greater than to this. Therefore, it is going to be inserted exactly like this. So it is a 3 here and it will come 2 dot, 3 dot. It will come here 5 dot, 15 dot and 25 dot. We got it is greater than 2, your P leaf that is equal to 2. Therefore, once again, what will happen? There is a requirement of what? Split. This time, the middle element is going to up. So we got a new structure now. What is that? 315 towards to the root. 315 towards to the root. And you take this middle one pointer, middle one pointer. This is your root. Your root can have 3 pointers here. It's okay. Then left, and this is left, and this is this side. So you have to maintain less than is equal to, that is 2.3. We are not disturbing it. Now this is the point. What is that? You need to split exactly to lesser than is equal to. So these two will come into this side. So what is the value? That is a 5 and 15. So we got 5 dot and 15 dot. This is your lesser than is equal to, and greater than you have 25 dot. And these are your leaves. Now I want to insert 1. Now when you insert 1, this 1 will insert it there. 1 and 2 and 3. This is greater than your leaf. Again there is a requirement of split. So this time the 2 will go into the middle. Therefore you please observe 2 here, 3 here, 15 here. All of you please observe, friends. And there are block pointers like this. This is lesser than is equal to, up to here you need to maintain. That is 1 dot, 2 dot, and 3 will be separated. 3 will come here, and this is as usually 5 and 15. This is as usually 25 dot. Now you observe record pointers carefully. There is a record pointer, there is a record pointer, there is a record pointer. Now you see, friends, this is your data file now. Your data file is what are there on the leaf, that is only your data file. What are there on your leaf? Please see 1, and next immediately 2. We are not touching root and internal node, just I am bringing only from leaf node only. This is your 15, this is your 25. So we are not going to touch any root and internal node to pull the record. The record is going to pull only from your, what I mean to say, record pointers or data pointers which are available in your leaf node. So this is your leaf and this is your root. But there is a problem with root. What is the problem with root? The maximum block pointers I mentioned as 3 only. But here you got how many pointers? 1, 2, 3, 4. Therefore, this again further split. So 3 will go up, 2 and 15 will be your left and right childs, and leaf node is as usually. So this is your data file, how the records are going to be retried. Any doubts, friends? Now you observe, you got 2 different structures. One structure is root and internal node structure. One structure is root and internal node structure. So other structure is a leaf structure. So you please observe what is root and internal node structure. If a root and internal node structure has block pointer and keys. Okay, and here one more thing is that every of your leaf pointer will be integrated with other leaf pointer, that they are all available in ascending order. This is very important, this junction. So combining these are all very important. So as this is nothing is there, so it can be null over there. Now you see root order has m block pointers plus m minus 1 keys. Nothing else. This is going to be stored in your block. So please see, they are your duplicates. Please observe, friend. Root I am maintaining it 2, and leaf also I am maintaining it 2. Please observe carefully. 2 is maintaining in root and 2 is maintaining in leaf. 3 is maintaining in root and 3 is maintaining in leaf. And you see 15 is maintaining in root and 15 I am maintaining in leaf. There may be a chance of duplicates here. So both and two different blocks. Block 1 also we are maintaining, and these blocks are also we are maintaining. So how many blocks we have? So after splitting we got one root node, two internal nodes. So 3. And here this is a fourth one. This is a fifth one. This is the sixth one. This is the seventh one. So 7 indexed blocks and one data file like this. Okay. Now, so what is the leaf structure? You please observe. M keys I can insert directly. As many keys you want. M keys I can have. M record pointers I can have. Plus one link pointer. This link pointer is called as a block pointer. They have to be located in your block. That's it. So this is the representation how you could able to identify the degree of a node. Here M is nothing but P root. Here M is nothing but P leaf. So your leaf structure, you can write the formula using leaf structure. P leaf nodes are there and P record pointers are there and one link pointer is there. Therefore I have written that. So P keys are there, P record pointers are there, one link pointer is there, and we have block size. And here also you please observe root and internal node structure. Block pointers only keys, nothing else are required there. So only I am mentioning that block pointers, M block pointers, M minus 1 keys are represented in your block. So this is how you can able to construct B plus structure. Ultimately, you need to know about, so you need to have some basic knowledge. So whenever you have a time, once you refer, what is index, what is a single level index. If you come to the plus course, we will discuss all these things. And what is a primary index, and what is a cluster index, and what is a secondary index. These things is supposed to learn. Then after that, you have to learn about multi-level indexing. This is index over index. And after that, in this we are talking about your binary search trees and other search trees. And the other one, this is what? M-way trees. When you have M-way trees, it is a B tree and B plus tree and B star tree. Before that, you need to have a knowledge what is a data block and what is a index block. So please refer them. We will discuss deeply about this in your plus courses on. So any doubts you can post now. So we understand how to derive the equations I have shown you. So if you know the block pointer value and the key value and record pointer value, I can able to solve it. For example, you look at that. Your block size is equal to 512 bytes. Please understand, friend. Your block pointer is equal to 7 bytes. Key size is equal to 9 bytes. Record pointer is equal to 6 bytes. Dash is the order of a non-leaf node. Order of non-leaf node, when I mention, then immediately you need to use the structure of root and internal node only. What is the root and internal node structure? This is the structure. What is that? Please understand. M block pointers plus M minus 1 keys is equal to your block size. Therefore, you can write like this. M block pointer, it is a 7 bytes. M7 plus M minus 1. Your key size is 9 bytes. That is equal to block size is a 512 bytes. So I can write it is a 7M plus 9M minus 9 is equal to 512. So 16M is equal to 521, and your order of non-leaf node, is 521 by 16. So what is your M? What is your M? What is your M? You know, maximum number of keys, maximum number of block pointers in a root or internal node. So we got this M value using this equation. So okay friends, so we learned in this session why we are using the MV trees, especially B tree and B plus tree, and what are the two important differences. B tree does not have duplicates, B plus tree has got duplicates, but both are using the concept of log M of base n, where M is nothing but order of tree. And one common point there and here is that both are having balancing only, self-balancing. And next one, they are going to have the concept of MV concept. Next one, the keys are resorted every time using record pointers only. You can able to pull the records. This is the end of this session. So evening session we are going to discuss about problems on B trees and B plus trees like this only. So use the formula and pull the records. So tomorrow session is relational algebra. Day after tomorrow is a marathon session from 10 to 1. Okay. So we'll meet in the evening session. Thank you all.